Hello everyone, welcome you all in this video. Today we will discuss about nanomaterials. In this video, I will cover significance of nanoscale, then we will discuss properties of nanomaterials, and then after there are two techniques for synthesis of nanomaterials, that is top down and bottom up approach. At the last of video we will discuss about the applications of nanomaterials. So let us start the video. The American physicist Richard Feynman introduced the concept of nanotechnology in 1959. During the annual meeting of the American Physical Society, Feynman presented a lecture entitled "There is a plenty of room at the bottom." So in this lecture, Feynman made the hypothesis: why can't we write the entire 24 volumes of the encyclopedia on the head of a pin? And described a vision of using machines to construct smaller machines and down to the molecular level. So this new idea demonstrated that the Feynman hypothesis have been proven correct. And for these reasons, Feynman is considered the father of modern nanotechnology. So here, generally we use two terms, nanoscience and nanotechnology. So we should distinguish between nanoscience and nanotechnology. Nanoscience is the study of structure and molecular on the scale of nanometers ranging between 1 and 100 nanometer, and the technology that utilizes it in practical applications such as devices. So this was the basic difference between nanoscience and nanotechnology. Now we will discuss about the nanomaterials. Nanomaterials are classified into the three following categories. So bulk material has three dimensions. Out of that, when one dimension is reduced to nanoscale, say 10 nanometer to 100 nanometer, then that is called a nano layer or quantum layer, like thin film, surface coating. When out of three dimensions, two are reduced to nanoscale, then that is called as nanowires, like quantum well or quantum wires. And when all three dimensions are reduced to nanoscale, then that is called as nanoparticle, like quantum dots or colloids. Now let us discuss some nanostructures first. So different forms of commonly used carbon nanomaterials are basically graphene layer, fullerenes, and carbon nanotubes. So graphene is basically a single graphite layer of densely packed carbon atoms is known as graphene. When carbon atoms are arranged in a honeycomb pattern, as you seen in basically the diagram, it is very stable, strong and flexible, having dimensions of 10 nanometer to 100 nanometer. So due to high mobility and minimum resistance of electrons through graphene layer, it is very useful in transistors. Now, fullerenes. So these are basically obtained by rolling up graphene sheets into sphere. So buckyball is the smallest member of fullerenes family, and you can see the image of C60, that is basically known as buckyballs. So due to their large surface area, they are highly reactive and act as an catalyst. And the carbon nanotube. So carbon nanotubes are molecular scale tubes made by rolling up graphene sheets like a tube. Having outstanding properties, they are the stiffest and strongest fibers known and remarkable electrical properties. And we have discussed about the quantum dots. So a quantum dot is a semiconductor whose excitons, basically electron or hole pair, are confined in a three spatial dimension of nanoscale. So as a result, they have properties that are between those of bulk semiconductors and those of discrete molecules. So researchers have studied quantum dots in transistors, solar cells, LEDs, and diode lasers. So by using these quantum dots, you can produce different types of colors. Now we will discuss about the significance of nanoscale. So nanometer is 1 billionth of a meter, that is 10 to the power minus 9. So nanoscale enables researchers to utilize the unique physical, chemical, mechanical and optical properties of materials. So what is the effect of this nanoscale? So scale at which quantum effects dominant properties of materials. So nanoelectronics size of the devices is in the range of the de Broglie's wavelength of the electrons. You know very well about the de Broglie, that is lambda equals to h upon mv. So if you solve this de Broglie electron, de Broglie wavelength for the electron, it comes around 1 to 10 nanometer. So nanoelectronic size of the devices is in the range of the de Broglie wavelength of the electrons. So quantum size effect become relevant in those devices. And now the uncertainty principle is very important if we are considering nanoelectronics applications. For example, tunneling effect. You will know about the uncertainty principle, that is delta x delta p, the product of delta x delta p should be greater than a constant, that is h cross. Now scale at which surfaces and interfaces play a large role in materials properties. So how surfaces area will dominate the material properties. So in any material, atom on the surface behave differently from an atom within the bulk. So the difference is mainly because of their potentials. Now, as the size of the particle decreases in nanostructures, the number of atoms on the surface is in a greater proportion of the total number of atoms. So surface atoms start dominating the properties of whole material, and that give rise to the difference in the properties of the nanoparticles and their applications in different fields. So there are two effects we have discussed that affect the properties of the materials. Now we will discuss the properties of nanomaterials. So optical property, first we will discuss optical property. In metal, as size of the particle decreases, there will be an oscillation of electron gas takes place on the surface of the nanoparticles, which is basically known as surface plasmons. Now, when those nanoparticles are exposed to light of wavelength comparable to their size and frequency close to that of the surface plasmons, then surface plasmons would absorb energy and nanoparticles shows different colors. So that is the practical application of the nanoparticles. So by using this property, you can produce different type of colored glasses. Then electrical properties. So for any solid structure, the capacitance of the structure depends on the dimension. As dimension of the particle decreases, capacitance also decreases linearly. So for a very small dimension, the voltage change of the particle can be measurable even when a single electron added to it. So this is known as Coulomb blockade effect. Basically, it is utilized for making single electron transistor. So it is a a great discovery for using this nanotechnology. Now we will discuss about the magnetic property. So magnetic nanoparticles behaves differently than bulk materials. So ferroelectric materials smaller than 10 nanometer can switch their magnetization direction using room temperature. So thermal energy, uh, so making them useless for memory storage. You know about the block walls, and if the domains are aligned in a particular direction, they will show the magnetic properties. So if the thermal energy of the room temperature is shifting the direction of these domains, so they will not oriented in the single direction, and you can't use them for the memory storages. So mechanical property, Young's modulus begins to decrease as grain size goes below 25 nanometer. So there is a remarkable increase in yield strength. Copper nanoparticles smaller than 50 nanometer size are considered super hard metal that do not exhibit the same malleability and ductility as bulk copper. So you can see that the properties are changed, whether it is mechanical, whether it is magnetic or optical, when you reduce the size of the particle. Let us discuss the basics of synthesis of nanoparticles. So two main approaches are used in nanotechnology for the production of nanoparticles. In the bottom up approach, materials and devices are built from molecular components which assemble themselves chemically by principle of molecular recognition. And in the top down physical approach, nanoparticles are constructed from larger entities without atomic level control. So these are basically two approaches for the synthesis of nanoparticles, that is the bottom up or top down. Let us have some more idea about these two approaches. So I will use the laser pointer here. Yeah. So in the top down approach, you are starting with the bulk material. So basically this is the physical techniques, and it works on the solid material only. Or in basically the bottom up approach, you will start with the liquid or gases, while in the top down approach you will start with the solid. So this is basically the physical approach. You are starting with bulk, then by any techniques like grinding, crushing, ball milling, you will convert this bulk material to the powdered form. So transformation by energy, so you will apply, so you will get powder from the bulk material. When you convert this bulk metal to the powder, the properties of the metal is not changing too much, but when you convert this powder to the nanoparticles or nanomaterials, the properties will enhance a great. So in this top down approach, you are reducing the size from bulk material to the powder, then to the nanoparticles. While in the bottom up approach, you will start from the molecules or atomic levels, then by using different techniques or methods, you will condensation of these molecules into the clusters, and by the clusters you will synthesize nanoparticles. So there are two approaches to reach these nanoparticles, either by top down approach or by the bottom up approach. So in this picture you can have the idea of the different sizes. So in the top down approach, you are starting with the bulk material. You are starting with the bulk metal which is the size of around 1 centimeter. So by any method you are transferring this bulk metal to the powder form, that will be in the range of 100 micrometer to 10 micrometer. Now this powder form will uh, convert in the nanomaterial by the laser beam techniques or by the lithography or by the mechanical techniques, grinding, polishing. So this way you are getting the nanometal by using the top down approach. And if you start with the bottom up approach, then your atoms molecules are basically in the range of zero point 0.1 nanometer. So by using the bottom up techniques like a sol gel method, self assembly, organic synthesis, you will get the clusters of the size 1 nanometer to 10 nanometers. Then you will get nanometal from these clusters. So these are the basically two approaches, top down approach and bottom up approach for synthesis of nanoparticles. So in both the approaches you are having the different types of techniques. Now we will discuss about the applications of nanomaterials. So nanoparticles are basically considered if the size of the particle is between 1 to 100 nanometers. So if we discuss about the carbon nanoparticles, that is the uh, carbon nanotubes like that. So they are basically used in the drug delivery, biosensors, bioimaging, pollutant removal, fuel cells, photocatalytic reaction sensors and H storage. And if you are going to the metal nanoparticles like the silver nanoparticles, gold nanoparticles, platinum nanoparticles, so they are having their different uses. They can be used in nanomedicines, water treatments, sensors, antibiotic agents. Then gold nanoparticles can be used for the therapy like the photothermal, photodynamic, gene therapy, then biolabeling and biosensors. Like if you have nanoparticle composites, then they can be used for the packaging materials. So nanoparticles also have use in the basically medical field. So in nutshell you can say that nanoparticles are having the great applications in different type of industries like medical, automotive, automobile industries and other industries. So if you have any queries regarding this nanomaterials concept or any uh, theoretical background, you can write me in the comment box. Thank you for watching this video.